Right. All right. Okay. So, ready? You want to just go at it?
Yep. Yeah.
Great. Okay. All right. Well, I'll do this one. Good morning. It's my name's John Griffiths. I'm here. Thanks all for joining. Today's presentation is going to be part of the design guide for planning for disasters, and we're going to talk about power resilience, compliance and healthcare infrastructure. So with that,
these are events. These are event
oh,
slides.
okay.
So
All right.
you can just run through them.
Let me change that. Right. Okay, I bet. Now, I can't remember if we're going to introduce ourselves
He
or.
was going to say, and then I'll go ahead and have the presenters introduce themselves.
Okay. All right. Great. John Griffiths, electrical engineer, founder of Context CA. I'm also a member of the Hospital Buildings Safety Committee.
Hi, I'm Jamie Schnick. I'm a senior electrical engineer at OshPod. I'm a member of the Building Standard Units and serve as our office's technical lead for electrical.
I'm David Bliss. I'm the CEO and founder of Faraday Microgrids, which develops and builds particularly healthcare microgrids. I also happen to be a practicing surgeon in California and have been a member of the Hospital Building Safety Board in various capacities for the past 7 years or so.
With our first few slides, I'm going to be giving a quick history behind this year's webinar series on disaster preparedness. Starting with a little bit of history on our name and relationship between HCI, OshPod, and the Hospital Building Safety Board. Prior to 2021, we were known as OshPod, the Office of State Health Planning and Development. Our group that functions as the building department for hospital construction in California was called the Facilities Development Division. In 2021, the California annual budget, the addition of various services to OshPod resulted in a reorganization and rebranding of the office into a full department named the Department of Healthcare Access and Information, or HCI. In December 22, HCI transitioned its division's names within this department. At this time, the name FDD was dropped, and we were named the Office of Statewide Hospital Planning and Development. This you'll notice that we were the Office of Statewide Health. Now we're the Office of Statewide Hospital. Same acronym, OshPod, so we didn't have to change any of the banners in the code. So OshPod is an office of HCI, and therefore both OshPod and HCI are correct when referring to our unit that still serves as the building department for healthcare projects in California. Next slide.
All right.
Oh, sorry. Now, the Hospital Building Safety Board is an advisory board established by statute to advise the HCI director on application and administration of Hospital Facility Seismic Safety Act. Hospital Building Safety Board also acts as the Board of Appeals for hospital facilities for seismic safety and fire and life safety issues. The board is comprised of 16 members, 6 statutory ex officio members who represent different state agencies, and 3 additional ex officio members, all appointed by the HCI director. The Hospital Building Safety Board maintains close contact with professional groups, industry organizations, and it brings to the attention of OshPod various changes and emerging issues occurring in the design and construction of healthcare facilities. It was the Hospital Building Safety Board that recommended the creation of the design guide, planning, and preparing for disasters. Next slide, please. So, HBSB also recommended that this webinar series be developed to help announce the HCI design guide for planning and preparing for disasters. This guide was put together as a resource to study past unanticipated events that threaten the day-to-day activities of California healthcare facilities and to share lessons learned from them. The goal is to help facilities be better prepared for future events that affect hospital infrastructure and systems that serve these healthcare facilities. Next slide. The guide applies to new facilities and also major alterations to existing facilities. It is hard to design for unknown, That is the goal of this guide. It studies what can be done to increase flexibility in various design systems to adapt facilities access, utilities, and emergency projects while providing flexibility for future care options. Ultimately, this design guide demonstrates that designing beyond code minimum can help facilities be best prepared for unforeseen challenges. Next slide. The guide is designed to be used by owners, operators, design teams, local agencies, planners, contractors, and of course, anyone else involved in the planning of healthcare facilities. Next slide. We all still remember the COVID-19 pandemic, where we saw that most, if not all, facilities were essentially caught by surprise and were struggling to find ways to provide safe care environments for staff and patients. OSHPD was called upon to help mitigate and deal with some of these issues. As an example, how does a facility provide negative pressures for all patient care areas? How do facilities deal with surging number of patients above and beyond normal expectations, and so on? Ultimately, and as a result of this, there was some discussion if OSHPD was going to change the building code to incorporate these lessons learned. So OSHPD assembled a group of people knowledgeable in healthcare design, planning, codes, and regulations, and the Emergency Design Task Force was ultimately created. Next slide. This group was tasked with identifying not just things related to the pandemic, but also other disaster events such as wildfires and earthquakes. Interestingly, it was determined that for normal everyday operations, current code was adequate. But what about facilities that need to be designed to incorporate or accommodate disaster situations? Next slide. As a result, the design guide also addresses many options to prepare for possible future events. The technology, process, and lessons learned were incorporated into the design guide and offer options such as switchable air volumes, redundant services, and incorporating new technologies into practice, as this design guide tries to cover all of these things. Next slide. So, with that in mind, the guide has a great cross-sectional application. And these seminars, there'll be a total of 6 webinars that address different aspects and excerpts from the design guide. Today is session number 3, which addresses power resilience. What used to be a given that the electrical service to the site is reliable is not always the case anymore. In the last decade, we've seen more power outage due to wildfires and public safety power shutoff. In some areas of the state, it is not uncommon for there to be multiple events where utility power is unavailable from anywhere from a few hours to a few days annually. Next slide.
Right. Well, thank you, Jamie. That's a great introduction and overview of the, why we're doing these design guides and some of the challenges we're facing. So this is power. We're going to talk about power. So in terms of our agenda, we're going to talk about, what does resilience really mean? And we're going to touch on the, the threats that add to, build on what Jamie just mentioned earlier, but those are problems. What you want to hear are solutions and opportunities. And then again, coming back to Jamie, he's going to share some of the great work he's HGuy, and really Jamie's been doing, helping the codes and, really at state level, but also nationally. And then David's going to pick up, share some of his experience delivering some of his really groundbreaking projects, delivering more resilient and sustainable projects. And then my favorite part, is pick up on the Q&A at the end. And, as you go through, if you have questions, please put them in the chat, and interested to hear your comments and thoughts as we go through. So with that, let's jump in. So, we're talking, about resilience, but what we want to do in this presentation is break down, what does it mean to be in a resilient facility? We've got, current codes, in a hospital, that's pretty high level. It's a resilient facility, but it's a baseline. It says here, shelter in place. But what we're going to also talk about is really the goal is business as usual, if possible, and when you lose power. So we're going to talk about that, the goal of business as usual. What does that mean to continue to operate without power? So hospitals, right? Big generators able to operate for 96 hours, water, power, sewage. But, in reality, I'm sure many people in the audience here, when you have a hospital operating on a baseline or code minimum emergency power system, of course, couldn't have to put a code section in here, life safety. You've got 4 branches in the hospital. It's actually fairly basic lighting. In the corridors, it's going to be egress lighting, alarms, exit signs. The building's going to be safe. And in medical areas, the code minimum, you're going to be able to operate the medical equipment, lighting, some receptacles, and HVAC, supply, exhaust. A critical thing here that bringing awareness in a code minimum hospital is just chillers. When these power outages are happening in California, oftentimes it's during the hottest time of the year. You only have chillers cooling for surgical suites and IT equipment. And then we got there stairwell pressurization, not many high-rise buildings, but that's also there. And then 1 elevator per bank by code. So you don't have your full elevator backup. So that's code minimum. And in this guide is not really telling you what's in the code. What we want to talk about is, how do we get, these are the challenges we face before we start talking about enhanced resilient buildings. Right, so there's the code. Hospitals are operating within the constraints of the code, but there are also we're breaking down into internal and external threats. So what are the internal threats? So one of my favorite topics is electrical engineer, aging equipment, through no fault of the facility. And a lot of hospitals are built 50, operating now and delivering healthcare, built 50, 60, probably even older than that. But some of the equipment is working well beyond its design life, and it's because it's expensive and hard to change. Deferred maintenance is another internal threat. Maintaining a circuit breaker, operating them, it's challenging. Aging equipment, if you don't properly maintain the equipment, is it inherently makes it less reliable. And then misalignment of we call it misalignment design and energy intensity. What does that mean? Again, looking back, a lot of hospitals, the newer ones, are, who imagined the electrical design loads we have to design to now? Will the data intensity, when we look back, 10, 20, 30 years ago, when these systems and infrastructures were conceived, the power density was way, way less. So what is that relevant to this conversation? Hospitals are now having to operate supporting significantly increased electrical loads. And that all being said, so we've got these systems that will help us keep hospitals going. And key part of that is having good maintenance staff. And within the electrical and disciplines of maintenance, in California, there is a skill shortage. Right. So those are the internal threats. So when we just talked about what's in a hospital, what are the external threats that challenge the grid that supports a hospital? So the grid, right? So similar to the hospitals, we get aging equipment, and the distribution, there is being good work done now, but also demand is increasing. You can't look at a news article without hearing about the AI data centers increasing the load by a significant amount. And extreme climatic events. This year is predicted to have an extreme or an El Nino, and we're going to see, we're even now seeing much increased climatic events. Systems are going to have to operate at climate in temperatures that they were not designed to do for a prolonged period of time. So that's an external threat on the hospital. And then we have supply chain. Okay, if we have the money, we want to change it. Now, we have extremely long lead times. Again, most of what I'm talking about here is an electrical engineer, but we're seeing very long lead times on critical components because electrification and just still picking up from some of the manufacturing lags from COVID. So these are external threats. Even if you want to within the hospital, you can control that. These things are out of the facility's controls, but need to be recognized. Right. Okay, so that's the problem statement. What other constraints do we have? If we want to deliver that. So we're going to do something better about it. We've got cost, space. If we're going to deliver more systems to make the hospitals more resilient, we want to put solar on a roof. Well, many hospitals the roof is covered in HVAC equipment or parking lot. Parking's typically critically short in hospitals. So we're space constraints. And one of the big things here, maybe our call to action as we go through this, is delivering sustainable, resilient systems is the need for more seismically certified electrical equipment. So again, we can talk about that later, but if the system or distributed generation system is going to form part of the emergency power system, it needs to be seismically certified. We are seeing components come onto the market, which is great. Kudos to the firms that are doing that. It'll be great to see more. And then a fragmented design supply chain. When we talk about the other things, supply chain, getting these distributed generation systems and more resilient systems, people aren't so familiar with that because it's different. And these are some of the things that just make it more challenging to deliver it. All right, so that's the problem. What are we going to do? So we're going to couple as we go through this. Just talking a high level here. These are the problems. What you really want, I think, if I was on this call, I want to hear about what are the solutions. But solutions is the basic is supplement the utility. So it's simple to execute. You can back up the generation, the normal branch. But I think our stretch goal would be to have on-site utility to serve as emergency power system. We're going to talk more about that later. Right. So with that, we've got the solutions here, and I'm going to pause there. We're each are going to talk about these separately. Distributed generation. We okay with that, or I can just tee this up and hand it off to you, Jamie?
Yeah, I think I get the next slide, right?
Okay, right. So we're talking problems, touched on the solutions. So we're going to talk about distributed generation resources. HKI's perspective, Jamie's is going to pick up, and then David's going to follow up. Actually, I could probably lose this slide, I think. Right. Okay, right.
Sure. So we're going to talk a lot about healthcare microgrids today. And a quick little graphic, but a definition. A group of interconnected loads and distributed energy resources, DERs, within clearly defined electrical boundaries that act as a single controllable entity with respect to the grid. So I'm going to try not to read a lot of slides, but I'm going to read that. We see a lot of facilities that have PVs, that have fuel cells, but they're not configured as a microgrid. The microgrid, some of the benefits of the microgrid we're going to see is the ability to remain on in the event of a power outage, to transition into island mode. Next slide, please. This concept of microgrids has been, and distributed energy resources has been in the code for quite some time. We see Article 690 originated in 1984 on photovoltaics. Article 705, 1997, these are 30 years ago, which is microgrids. 692 for fuel cells. And again, what's brand new is microgrids as an essential electrical system source, which was introduced into our code, our California Electric Code, in 2022. Next slide. So we know that the slides permit them, and the great benefits as far as resilience and hardening your facility allows this island mode capability. It takes off some of the strain that's on the electric grid by having on-site power generation. And by having multiple sources, it increases the reliability in that some of these sources could continue to operate in the event of a failure of one or more sources. Next slide. As John said, implementing microgrids to help, harden the electrical facility, there's two major options. One is on the top, supplement the utility to be a supplemental source to the electric utility, and the code requirements can be found in Article 705, which is called interconnected electrical power production sources. The other option is to utilize the microgrid as essential electrical system. And again, this is permitted by code, and you'll find the requirements in the California Electric Code, Article 517.30. Next slide. So I'm not going to dwell on this, but there are a number of requirements to incorporate the microgrid to supplement the utility. For an existing facility, you need to take a look at, obviously identifying the sources. We want to make sure that the responding fire department knows how to de-energize the electrical system when necessary, all of the systems. The bus rating, marking a disconnect. So this is a very straightforward, I believe, code requirements on what's required when you're implementing microgrid at your facility. Next slide. The code as written, and this is language that was put into the national code and was adopted by California, it says that the requirements for microgrid to serve as an emergency source, they need to be sufficiently reliable for healthcare to use them. So what we identified in the OSHPD CAN is, what does that mean? Number one, just like the generators, if you're going to replace the generators with other sources, they need to be specially seismically certified. Number two, they still need to follow the NFPA requirements for that particular source. The NFPA 111 is written strictly for batteries as essential electrical system. NFPA 853 is fuel cells. They need to be classified as a type 10 class X, which means they would start within or assume the essential load within 10 seconds and would have the operating runtime specific to their class. For hospitals, that's typically 72 hours. And also, we're going to require that a sequence of operation and thorough commissioning takes place under our observations, so we can confirm that the system will operate as intended. Next slide. I want to point out that initially there was concerns from CMS because they adopt an older version of NFPA 110, but you'll see that in 2023, much assist by our group, essentially Walt Vernon, who's not here, has been pushing and helping the code evolve to accept these emergency power sources. This categorical waiver does allow microgrids to be the emergency source on your healthcare facilities. Next slide. We talked about the pin that we put together. We also developed at OSHPD a guide. Our A7 guide is entitled Microgrids for Healthcare Facilities. And this guide is intended to help people understand what they'd be getting into and how to navigate the various challenges of implementing a microgrid at their facility. Next slide. You'll see one in the first section. We identify a number of code requirements. It's pretty small, hard to read, but we start off with CARB, the California Air Resource Board. If you're going to be burning fossil fuels, you need to meet their requirements. The CPUC, which is the utility requirements, they have a Rule 21 where they strictly require that you're not backfeeding their systems. And then all the various NFPA and NEC and California electric codes that are based on the type of distributed energy resource you would be implementing. So first we list those, all that we could see that could come into play. Next slide. And then we run through a number of examples. In this case, you'll see the proposed example is the code-mandated emergency system is in place, and this microgrid is supplementing the normal side. And as you go through the next slide, we'll basically, okay, so I'm sorry, back up one. So go ahead and back up one. So what this guide does is it kind of walks you through. And remember the big code matrix that we showed, it basically shows how you would pare down that code matrix to customize for your project. And then it gives a lot of hints along the way. For instance, the utility company and their Rule 21 is pretty complicated and drawn out process to get that approval. Sometimes you've seen that extend over 2 or 3 years. So it kind of helps share what we've heard from lessons learned and guide people through the process. Next slide. That first example was for acute care hospital. We also, profile what it takes to implement microgrid at skilled nursing facilities, clinics, psych hospitals. In general, we look at first, supplementing the normal system, and then second, what codes would come into play if it's going to replace the essential electrical system. Next slide. So we want to just share, permitting of microgrids is achievable at healthcare facilities. Dozens of projects have been installed with distributed energy resources. And under current codes, they can be configured to not only to lower energy bills, reduce the carbon footprint, but provide that resilience that we're looking for. Next slide. And then finally, permitting microgrids as essential electrical system source is also allowed by code. This is more challenging, and we've walked through and we've seen a number of projects. David's going to go into some that are taking steps to make these projects a reality. And some of the things you'd have to look at is, we talked about special seismic certification, commissioning, and on-site fuel storage. We'll go ahead and pass it on to David now.
Thanks, Jamie. I first want to give a compliment to my co-presenters, Jamie Schnick from HKI Oshpod and John Griffiths. To the community that we're presenting to, I would emphasize a couple of things as a developer, builder, and even owner of these systems. First of all, HKI is and to advance high quality, safe projects, and expert design personnel like John are really key in your selection of a team in terms of designing these things. Next slide, please.
Oh, no.
This is an artist's mock-up of a project that my team developed and built and owns and operates at the Kaiser facility in Ontario with CEC funding to create it. And this is about a 2 megawatt solar, 1 megawatt fuel cell, 8.5 megawatt hour battery system. You'll notice here the batteries are stacked to utilize the space best. As an example of space utilization in existing facilities, because you have different design priorities in the built facility versus the facility undergoing design, we took a detention pond for water and converted that to a concrete pad that we could build upon. And this allowed us to then put the microgrid in right next to the central utility plant for the most effective and efficient manner of doing this without taking any useful space away from the facility. Because as you know, parking is a luxury. So this is designed, this is interconnected, and it's the first of its type in California, interconnected to the critical branch of the hospital and designed to be able to operate in parallel to the utility during utility outages and to maintain the performance of the solar, the fuel cell, and supplement the diesels as a next phase demonstration of capacity to support hospitals through these situations. And to go back to something Jamie commented about, the code requires that you have two independent resources to be able to fully operate the hospital for emergency, in case of emergency. In this case, the microgrid becomes, in essence, a second resource on top of the existing diesels. Next slide, please. Valley Children's took the step to be the next generation microgrid facility, and they are going through a two-phase development, the first of which is a large solar array and fuel cell intended to supplement their existing power and minimize their reliance on grid power. You can see the design of the giraffe, which is their emblem for the facility, with the facility in the background. That's actually the solar array. This will be supplemented by a large battery system that's being paid for by the California Energy Commission that should be around, I believe it's 15 megawatt hours is our current design parameter. That's under development as we speak. And again, is designed to allow the hospital to have greater operational flexibility in emergencies, and also to do some of the critical things like demand management and even ancillary services to the utility, which for those of you on the finance side of healthcare will recognize as ways to recognize more revenue for the facility or to diminish facility costs substantially. Next slide. One of our colleagues, Salas O'Brien, was involved in the creation of a fully electrical system at the Kaiser facility in San Marcos. This was a new facility design, and so Salas O'Brien was able to work with Kaiser and with the design professionals to put together all of the equipment to be able to support the hospital, and also to make most of the systems within the hospital as electrified as possible. And this is operational and is, I believe, the first of its particular type. Next slide.
Wow. Well, great. Well, thank you, David. Thank you, Jamie. Fantastic overview. So in wrapping this up, we just want to go over, I laid out, I guess, Jamie introduced the, why are we doing this design guide? We talked, some of the constraints and challenges, but looking forward, we've got here hopefully David's going to talk about shared, it is possible to deliver sustainable, resilient healthcare, using these, where the whole facility is able to operate using these systems. Jamie, thank you so much again for helping us, allowing it by code. And in terms of follow-up, what's a call to action? So, we just want to, in this one, we wanted to highlight what it meant, what our existing code hospital looks like, what can be done, and what are the steps to do that. So with that, we'll switch to questions and next steps. All right.
Okay. So that was about 30 minutes.
Okay.
I timed us. Okay. Which is to say, I think that's good, right? We don't have to be any longer, but we also do have time for more. Okay. If you want to editorialize or amplify, we certainly have room to do that.
Yeah.
This is Yvette. Can I jump in really quick?
Yeah, right.
I think it'd be really fantastic if you could, because AIA is giving us credit based on what we told them this thing will last, including Q&A.
Okay.
So just want to throw that out there. Thanks.
Well, if you guys like, one way I could add to mine is to go deeper into the finance aspects of how this is paid for and what the revenue resources are and that sort of thing. I chose not to here, but I can add that very easily without having to add a slide.
Yeah, I'm thinking, I was really rushing on the first piece. It was 8 minutes, and the second piece was 11. So if we're looking at doubling our time, is what you're saying. So that was, I can go 10 minutes and 15 minutes is what I'll shoot for.
Great. And then David, do you think, I'm very aware, the Ontario is sort of it's the pinnacle. Can you sort of talk more about, because if I was listening on the presentation, that's pretty cool. Talk more about the components, or
Sure. You meaning more detail about the specific battery or the specific fuel cell, or more the how that all works together,
Yeah, um,
or both?
I think both. Just what you started off with a Kaiser Template Hospital, and what you ended up with is, with code systems, what you ended up with is a system that can island, or it's
Hmm.
but you've also integrated existing assets, the fuel cell,
Hmm. Yep.
and then the battery technology. Um,
Yeah, I'm thinking that, David, when you get it, you'll be able to look at your watch and see where we're at, and you just use it up, get to that
Okay.
hour. I- In my mind, I made some notes, um, but yeah, I think you could certainly spend more time
mm,
on both Kaiser and both of the Kaiser projects. Like,
mm,
I think for the first one,
Sure.
it's it's really important to say, um, this is a demonstration project. You're reaping all of the benefits of having the on-site resources that knock down your maximum demand and operate 24/7, but you're also demonstrating how they can assume the emergency loads, um, because that's one of the challenges, right? It hasn't been done before, so to be able to demonstrate that is a
mm,
huge step
mm.
in the evolution of incorporating microgrids to replace our emergency power sources.
Yeah, I suppose I meant to sort of talk about the evolution from conceiving of Richmond to then what we've done at Ontario. So I that's an oversight on my part, and I'll incorporate that. And if I don't, interrupt me and say, Dave,
Yeah.
what about the process of evolution from those
Okay.
Yeah.
things? So maybe I'll talk about the technical / code evolution in parallel, and then sort of say, and so all of that's great, but how do you make this work both in terms of financing it up front and downstream, recapturing that value in its performance? So I will do both those things.
So on the Kaiser San Marcos, I sat in on, or actually I co-presented with Duke Bowie on that, and
Yeah.
there's a couple things I wanted to share with you. Um, Number one, I would get away from, I never heard, this is a fully electric hospital. I know that, that's where Kaiser's going, and that was the UC Irvine, but I never heard that stated about Kaiser San Marcos.
I
I
do.
think
Yeah, I
the
don't
big
think it is.
the big thing to point out about Kaiser San Marcos is it's a 1.7 megawatt fuel cell that is sized adequately to back up the entire campus.
Yeah.
And so what happens is they have, a full complement of emergency generators, and they have this connected to the normal system. So in the event of a power outage, it's a seamless transition, and the occupants don't know that they've lost utility because the fuel cell assumes, the microgrid assumes all the load. And what we saw was that during commissioning is that the generators start, but they never pick up the load. So they're there, available, but and the signal is sent as soon as utility is lost. But because of the seamless transition to the fuel cell, to the microgrid, it then assumes all of the load, and the generators never, the transfer switches never transfer to the emergency generators, and then it carries. And one of the, great benefits that we hear from Kaiser is that now they don't have to reschedule surgeries. Now they don't have the, a real outage condition because nobody knows. And basically the requirement to have two sources always available, for emergency power as a minimum requirement to continue surgeries as normal.
Mm.
They meet that criteria by virtue of microgrid.
One clarification, Jamie. I want to make sure I understand the technical aspects. The the balloon fuel cell is not seismically certified, so it's connected on the utility side of the ATSs, correct?
Correct.
So if it's going to operate when the grid is down to sustain the facility and keep the ATSs closed, how does it address the anti-islanding Rule 21 issues?
It's the it turns off, it disconnects. So there is a period of time, there is a few cycles where there is no power. So they have
I guess
a
if I
relay.
can interrupt,
Yeah, okay.
sorry, because I think we're going to get asked this question if we go down this pathway. So if the implication is that the hospital can operate in the emergency mode with the fuel cell, right? Then the fuel cell is on the normal power side of the ATSs. You have two problems. You either can't operate during an emergency because of anti-islanding provisions of Rule 21, or you have to have some kind of secondary disconnect from the utility that allows you to be mechanically islanded. Otherwise, that's not going to be allowable.
Right. So what he did was, so it doesn't serve as the emergency source. It serves as the supplementary normal. And what Duke did was he couldn't get, and this is just in between us, I won't say,
Yep.
he couldn't work through the Rule 21 thing.
Yep.
So what he did was he said, okay, we'll disconnect. So there's a number of cycles where you are disconnected from power, and the fuel cell goes into an idle mode, and then it's transferred. So that's why the generators start, because they see that there's no power on that normal bus. But
what I mean is, though, but where does it transfer to?
What's that?
Where does the fuel cell, if the fuel cell comes back up, where is the power being injected?
At the normal source. It's on the normal source board. So the normal service has a 12 kV distribution board, and one of the inputs to that is the fuel cell. So it has a relaying scheme that disconnects it, so the bus is dead, and then reconnects it quickly.
So if it reconnects while the utility service is down, then that's a Rule 21 violation.
So it opens the main, right? So there's a utility service has an incoming breaker.
Okay. That's the part. That's the key piece.
It's what's called a break before make, right?
Yep.
So you break that. You open the utility main breaker.
I got it.
And then you close. So now you're in island mode.
Right. Okay. So
like I said, there had to be a mechanical break in between the fuel cell and the utility. That was the missing piece that I didn't hear. So I got it. All right,
great. Can I? Well, it's good to talk about. Can you get a single line? I guess if we can sort of talk offline or whatever. We can't get drawn in. I'm just mindful. I have a hard stop at 11.
So as do I.
So so glad we did this. I guess the other purpose of doing this was to test the GoToMeeting system. The GoTo. I just, my gut feels we're not going to have time to do it now.
I agree. We're going to call in tomorrow half an hour early and sort through that. And then I think is I'm going to be driving. Is that still the plan?
Yeah. So I am so sorry about that, you guys. I didn't realize I had to start the meeting on my end. So sorry about that.
No worries.
Yes, I'm logging in tomorrow and starting our session at 9:30. So anytime after that, but no later than 15 minutes before it starts, which is 10 o'clock. And then I don't know. Do you guys have any more updates to this presentation, or is the last one that I received from John the very last one?
No, I had a code error in mine, so I modified it. I made some really minor tweaks in the slide. It was just life safety. What I'll do, Yvette, as soon as we're done here, I'll upload it to Dropbox.
Okay, great, because it becomes the handouts for tomorrow, so I need to convert those over.
Okay.
Perfect. Okay. That's all I had. I am so sorry about today, but yes, I'll be on a half hour early, so you guys join.
I think we'll be able to sort it out tomorrow. I mean, I've done this a bunch, and once we get it all sorted out, I did have a couple more things to
Okay.
critique on you, John, and if
Yeah,
anyone
yeah.
has any for me,
I was
please
going to
share.
ask that.
So I think it's important to say, yeah, here's the code and here's the requirements. There's 3 branches. You said 4. There's 3 branches of the essential electrical system. The life safety is essentially what we see in emergencies for all the other buildings, and that protects the occupants. The critical branch is for patient care. And then the equipment branch is for large motors associated with patient care, pushers and stuff. So you get a little mixed up. The one thing I would say, and I don't know who's going to be there, but, you say it's hard to find good maintenance people. Well, I think it's better to say, typically the maintenance, is the first thing to be cut, when everybody's trying to manage these tight budgets. And so to have a robust maintenance program is super important. And we see that sometimes that's neglected.
Okay. All right. Well,
Anybody have
thank
anything
you.
for me?
Yeah.
No, I thought you did a great job, Jamie. It was thorough, and I think it hit the spot, in my opinion.
In my mind, I want to try to do a little bit more of this is geared towards, power resilience and get my vocabulary right. But so it's like, okay. So anyway, that's my thing. Thank you.
And the same here. Thank you for the feedback. I'm like, as I'm doing it myself, that could be better. And then, I'm trying to say, what is just thinking about, I was doing it before, what is our mission here? What does our audience want? And I guess we're doing it
Don't
tomorrow.
feel bad. I thought it was good. I think now that we know that we can all expand a little bit.
Yeah.
And David, since you're at the end and you can add or subtract to, I think you can just make up the time that's necessary.
Yeah. Well, we could talk all day about just like San Marcos switching, right?
Yeah, exactly.
Well, I mean, I would spend more time talking about your project that you're most familiar with. I just kind of wanted to give you the couple of those, but
yeah. Well, appreciate the time, guys. I have to jump off for another call,
likewise.
but I will see you guys first thing in the morning.
Thanks,
fantastic. Great. All right. Good job. Thanks all. Thanks for that.
Bye now.
You good, John? You got everything?
Yeah, good. I got. Yeah. Thank you, Jamie.
Thanks.